for quite a long time, and there was quite a lot of disbelief if they will ever work. However, they really work, and they have detected gravitational waves, and the sources of gravitational waves come from catastrophic events in the universe, like mergers or collisions of black holes. And how do we know about that? So there are these instruments. There is LIGO. There is also an interferometer in Europe called VIRGO. But let me talk about the event from 5 years, or now from 6 years or 7 years ago. So in 2015, the instruments have reached quite a high sensitivity, and this is the plot that shows the sensitivity as a function of frequency for these instruments. So this is the displacement spectrum, this is the frequency. Essentially, this value tells you what is the measured amplitude of displacement between two mirrors placed 3 or 4 kilometers away using precise interferometry and laser beams. And this means that these instruments are able to measure the displacements of the order of 1/1000th of the diameter of a proton between two mirrors spaced 3 to 4 kilometers away. So this is an unprecedented, precise measurement, and it's very difficult to imagine something more precise than that. And the reason for this is that we really need to measure small amplitudes, because the amplitudes expected for gravitational waves are really small. So in 2015, we have seen the following event. So these are the waveforms that have been measured in the two detectors, two LIGO detectors. This is the, okay, these are their time spectrograms. So this is the spectrum. Here we have the frequency, here we have the time. The spectrum as a function of time. And these two events that were measured in two detectors look like they are similar. So first of all, we can think that they come from the same source, that there is really one external source, and not just two independent disturbances by noise caused by whatever, by somebody passing or jumping in the vicinity of any of these detectors. And since this frequency range is also in the audible frequency range, you can convert it to sound, and you have heard the sound of these events just a moment ago. So we have these events, and if you overlay them here, you see that they are consistent with one another. So that tells us that we may have an event that is cosmic. So first of all, the events were significant in both detectors. The time delay, the time difference between the two was shorter than the time of flight by light between the two detectors. The two detectors are spaced 3,000 kilometers away, which corresponds to 10 milliseconds of light time. So if you put the source somewhere in the sky, the time difference, time of arrival difference, has to be smaller than 10 milliseconds. It was 6.9 milliseconds. And then we have this funny way that the signal behaves, because you see that the amplitude of the signal increases up to a certain point, then there is a sudden decrease. But also, if you look at the spacing here, the frequency tends to increase as the amplitude increases. And if you look at a typical physical system, this is not something that you very often encounter. The typical behavior of a disturbed system, like a bell, is that you have a constant frequency and a decreasing amplitude. And this is something completely different than seen here. A behavior like that is characteristic for gravitationally bound systems. If you, in a gravitationally bound system, this is kind of a weird system from the physical point of view, because if you take away energy, then the system becomes more compact and it starts to rotate faster. So you take away energy, but the kinetic energy has to increase. So you could say that it's a system with, that gravitational systems are kind of systems with negative specific heat, because you take away energy, but their temperature grows. And this is something like here. We see that we make the system more compact, the frequency increases, but when the frequency increases and we take away the energy, the amplitude or the strength of the interaction between the two masses, as we think, is much larger. So this is why we think that this is a gravitationally bound system. Now, significant in both detectors, signal shape is the same, delay is short, so it's a real astronomical system. So now, no, that's not this. Well, that was not supposed to be here. That's something that came here from the end of my talk. So then the question is, what is it? How can we find out what type of a system is it, and what does it correspond to? So in order to do that, we can do a simple analysis of this system here with, we can measure the amplitude even with a ruler, and we can measure the moments that the signal passes through zero, and we can then estimate the frequency of the system as a function of time, and then start to think what it could be. First of all, we can look what is the highest frequency that we have here, which corresponds to this part. And we can say that if it's a gravitationally bound system, we can use the Kepler's law to find out something about this system. Yes? So we can use our eye and we can measure the oscillations, the increasing frequency, the increasing amplitude, quick decay, and we can find out something more about orbital motion that corresponds to such a system and the sources that can exist over there. Good. So here we start. This is the moment where we have the highest frequency. We find that the minimum period here is about 7 milliseconds. So the gravitational frequency here is 150 hertz. Now, if you look at the expected gravitational frequency from a system, it is twice the orbital frequency. And this is because of the symmetry of the system. So trust me on this, right? So the Keplerian frequency of this system, so 2 pi, the frequency, gravitational frequency over 2, is 2 pi 75 hertz. And we can use the Kepler's law here. We know that omega must be equal to square root of gm over a to the third, where m is the total mass of the binary, total mass of the two components, and a is their separation. We assume circular orbits, and I think that it's a good assumption here. Let's not worry about ellipticities and all the complications. So we have some constraint between the mass and the orbital separation in this system. Now, if we have this, we would like to break this, but they are degenerate. M and A are degenerate. We only have a constraint on the two of them, but we want to break and find something about A and M separately. So in order to do that, we can do a little bit of math, and I was just worried about putting a few formula, but since you're all physics students, you are not scared with formula, and so I'll go ahead and do it. So the easy calculation is as follows. The gravitational wave luminosity, so the rate of the gravitational wave energy loss from a system, is given by this formula where this is the total mass, this is the reduced mass of the system, this is the orbital separation, and there is this G4 over C, G to the 4, C over 5. The energy is equal to this, so if we differentiate this and equate the change of the orbital energy to the orbital energy loss rate, we can, and we use the Kepler's law, we can find the following equation that governs the evolution of the frequency as a function of time. And you can take a piece of paper and do the calculation. I think that most of you will do it in 5 minutes. The point is that this equation is relatively simple. It's the first derivative. There is a constant here that depends on the mass, and omega in some power. So solving an equation like that doesn't require a lot of skills, is really, really easy. And that's what we'll do in the next step. So we have the, well, that's part of my Polish lecture. So that's the frequency change rate. Well, we can convert the equation we had before into an equation between the frequency and the frequency derivative. And then we solve it, and we find that the solution is as follows. That the frequency in the power of minus 8 over 3 is a linear function of time. And the coefficient here, well, apart from all of this garbage, is just proportional to mass. So if we do something very simple, like in the lab 1 of physics studies, so we try to fit a straight line to some points, we can have, if we plot this versus time, we can get the slope, and the slope will give you the mass. So let's try doing this. We can get the data as follows. So here, for each oscillation, we have t. We have the time t, and we have the width, which is delta t. We invert delta t, we get the frequency. So we have the frequency as a function of time. Then we take frequency in the power of minus 8.3, and we plot this versus the time, which we have here. So these are these green points. So this is the frequency in the power of minus 8.3 times 10 to the 5 to make it nicer as a function of time. And as expected, this quantity is decreasing, is following more or less a linear trend within the error bars apart from this point. But if you have so many points, one of them must be an outlier, so it's kind of obvious. And you can fit a straight line to those points and obtain the constraint on the mass. So this line corresponds to the chirp mass of 30 solar masses. This line corresponds to the chirp mass of 40 solar masses. And this best fit line corresponds to the chirp mass of 37 solar masses. So let me remind you what is the chirp mass. Chirp mass is a combination of masses of the two objects that comes out naturally in gravitational radiation physics. So if the masses are identical, the chirp mass is about the fifth root of 2 times the mass of each individual component. So it's close to each of the components. So if the masses were were equal, then both of them would be this factor times the chirp mass, and they would be 42.5 solar masses. So with this, we can break the degeneracy, and we have two constraints. We have now an estimate of the masses of these objects, about 40 solar masses, two objects of the mass of 40 solar masses, and we had the Keplerian frequency when they were at the closest approach. Yes? And this Keplerian frequency depended on the mass and on the orbital separation. So from this, we can get the orbital separation. So let's look at what does this mass imply. For a gravitational object, we can define the quantity called the Schwarzschild radius. And I understand you heard about Schwarzschild radius. It's this characteristic radius of a black hole with a given mass of the horizon. It's 2 gm over c squared. So, and in more of the standard units, it's about 3 kilometers for a solar mass. So for 42 solar masses, it's about 125 kilometers. So it's slightly more than the distance to Warsaw from here. Then, knowing these masses, we can find the orbital separation by just inverting the Kepler's law, which is basic high school physics. And we find that the orbital separation is 370 kilometers. So like Warsaw to Kraków, maybe Warsaw to Zakopane. And it scales very weakly with the total mass and a little weaker with the frequency that we had over there. So essentially, we have solved it, right? We have the masses and we have the separation. So let's look what this could be and how this object would look like. So we have an object 1, which with the gravitational radius of 125 kilometers, another object with the gravitational radius of 125 kilometers. They are spaced 370 kilometers away. And for this, we can calculate something called compactness, which is the ratio of the of the radii of this Schwarzschild radii of this system to the orbital separation. It's 0.45. It means that this entire system is extremely compact. And we can find out that at this moment, the velocities, the orbital velocities of the two objects, which we think must be black holes, must have been about 0.6 of the speed of light. So the only objects that can fit in with such mass, that can fit inside such a small orbit are black holes, because we do not know any other objects that could be stable and that could have such masses and such small radii. The other compact objects that we know, that is the neutron stars, have masses up to 2.5 or so solar masses and have radii of about 10 kilometers. But they cannot exist with higher masses because they become unstable and they collapse. And this is because they are supported by the pressure of degenerate matter, and this doesn't really work so strong against gravity above say 2.5 or so solar masses, so they have to collapse then. So in this, we see that we had a system of two black holes that came very close to one another and most likely merged. So I have made an assumption that the eccentricity of the system was 0, so the orbit was circular, and that the masses were equal. And here we can see what would happen if the mass ratio was not unity and eccentricity was not zero, then this compactness is defined as inverse of what I know. No, this is the same. As inverse of what I had. Then the compactness would be different, and this objects with compactness below unity cannot exist. They would have to be black holes anyway. So I think that this shows that in this simple estimate that I have made, we are relatively close to what the real properties of this source were. So we have a system of two black holes that are merging. So now, given this waveform, can we say anything about the distance to the source? And it appears that, of course, we can. And the one point of merging black holes is that, as in many phenomena in general relativity, there is very few parameters that determine the properties of the source. The main parameter here that determines the properties of the source is the mass, right? And the mass determines both the time scale of the orbit and the amount of energy that is emitted in gravitational waves. The amount of energy is a fraction of the mass, and it doesn't depend on the mass what fraction. The fraction is the same no matter what the mass. If we increase the mass twice, we will always get, everything will scale up. So if you see that the time scale is proportional to the mass and the energy emitted is proportional to the mass, you divide the two, you get the luminosity, the power that is emitted in gravitational waves, the amount of energy per unit time. And because of the scaling, this luminosity doesn't really depend very much on the source. These sources are therefore called standard sirens, because of this shape of the waveform and the sound that they give if we connect them to a speaker. This and the standard is like that they are not just standard candles, but standard sirens. So the way to do that is, if we look at this waveform again, we see that the maximum amplitude here was about 10 to minus 21. Then the estimate of the h dot, the first derivative of the amplitude is h times omega. We have the omega, we have estimated the omega. And a basic GR course will tell you that the gravitational wave luminosity of such a system should be proportional to the integral of this quantity times over a surface. So you can estimate it to be the following, where this is c to the 5 over g, which is a very interesting quantity by itself. Then we have the luminosity distance, the amplitude, the frequency divided by 4c squared. Now, if we know what is the luminosity of this system, the intrinsic luminosity of this system, we can, and this is based on measured quantities, except for the luminosity distance, then we can find what is the measured flux on Earth, which is this quantity. And by comparing the two, we can find the distance to the source. This distance to the source, it's just like a standard way of measuring distances in astronomy, that you compare the absolute luminosity with the observed flux, and by comparing them, you find what was the distance to the source. So we find that the distance, I think, is about 300 megaparsecs times and it scales with these two quantities in the power of -1. Now, this luminosity that appears here is kind of a very interesting quantity in itself. It's called the Planck luminosity, and essentially it's the largest power or largest luminosity an object can have if quantum mechanics and GR works, because that corresponds to a black hole of the size of a black hole that emits all of its energy in the time corresponding to crossing time of the horizon. And that doesn't depend on mass, and it's C5/G, so that's the largest luminosity an object can have in the universe, regardless of its size. So just as a side comment. So we have now obtained the distance to the source. So we know the masses, we know the distance, and we know, so the thing that we would like to know now is if we can find something more about the source and more about this new black hole that was formed. If the two black holes merged, then they formed another black hole, and there is a little hint of the activity of that new black hole that formed after the merger. This is shown in this very end of the waveform that we see. If you look at this part of the waveform, you can see that now the source starts to behave like a proper physical system that has the constant oscillation frequency and decreasing amplitude. It looks like a perturbed system. It looks like something that was perturbed. And in fact, it is. If a new black hole is formed, it's not in its equilibrium state, which would be a rotating black hole, like a Kerr black hole. It is a perturbed black hole, and it has to radiate away its non-sphericity. And this does this phenomenon is called the ring down of a black hole. The analogy in the real world that I find to this is if you go to a park and sometimes you see children playing with huge soap bubbles. These huge soap bubbles oscillate, right? Because they want to be circular, but they are formed non-circular, so they oscillate and try to get away of its excess energy. And the black hole, newly formed black hole, does the same. The horizon is non-spherical, and it radiates away its energy very quickly, as you see here, unlike the soap bubbles. So we have the constant frequency and quickly decreasing amplitude in this quasi-normal oscillation modes. And this, the frequency of these modes and their decay time can be estimated by analyzing the Kerr solution. And it depends on the mass as well. So by analyzing this part of the waveform, we can find whether this entire waveform is consistent, whether the mass that we expect from the in-spiral phase, that we estimated from the in-spiral phase, corresponds to the mass that we see of the final black hole here, and it does. So we see a frequency of about 200 hertz with the damping time of 5 milliseconds, which corresponds to the mass of about 80 solar masses, which is 2 times the mass of the individual components. Okay, then the position in the sky. This is something that as astronomers like to pinpoint things in the sky, and the gravitational wave instruments are essentially like directionless, slightly direction microphones. You know, it's like if I talk like this, you don't hear me. If I talk like that, you hear me a little better. But if I have 2 microphones spaced at some distance, then I can measure the time delay between arrival of my voice in 2 microphones and do this triangulation, and from just detecting it with 2, I can get a ring in the sky of possible origin direction of the signal. If I have 3, I can have 3 rings, and they will provide a position. But there is an assumption that is now justified, that the speed of gravitational waves is equal to the speed of light, and we now know that it is. But at the time of the first detection, we only hoped that it would be. Then the point is that not all the directions in the sky have the same weight, because the detectors, as this microphone, don't have the same sensitivity depending on the location in the sky. So we know that some locations are more probable than others. So in the end, we can use this geometrical factor that shows the sensitivity of the gravitational wave detectors, and we can exclude some regions of the rings in the sky as the possible locations. Now, so essentially for this first source, we got this type of a part of the ring with the most probable region being there, but it was kind of large. And if you do a proper analysis, not just like few lines on a piece of paper like I did, you can get the following results. The one mass is about 36 solar masses, another is 29 solar masses. The final black hole is about 62 solar masses. And for those of you who do quick addition, you can see that mass is not conserved here. And it's not a reason to be worried, because energy is conserved, because at this event, a few solar masses of energy were emitted in gravitational waves. So if you take them into account, everything is fine, energy is conserved. The final black hole spin, I didn't talk about it, it's 0.67, but typically if we have a merger of 2 black holes, the amount of spin or angular momentum that we have in the orbit corresponds to about 0.7 of the in this dimensionless units. We estimated the distance to be 300 megaparsecs. It's now 400 megaparsecs, so it's not so bad. So I hope that I have convinced you that with a simple back-of-the-envelope analysis, you can go from an in-spiral signal to real physical parameters of a binary and to find what kind of systems we are seeing. That's correlation between these masses. So okay, so in the end, the event that we saw can be visualized here as a merger as the final 0.3 seconds of a merger of a system that probably took about 1 billion years to merge, where you see 2 black holes in the very last moments, and these are so this is the visualization of the potential, and here we see the surface of their horizons. And at some point, this potential is becoming lower and lower. They are getting closer. And we see that the new appears, and it radiates its quasi-normal modes, and then we have a new black hole which is essentially quiet in gravitational waves and will be so for quite a long time in the future. So, okay, currently, this was the first detection that we managed to have in 2015, and since then the detectors have been working for quite some time. They have also been working in as a network of 3 detectors with LIGO, 2 LIGO detectors and the VIRGO detector. And we have had a few, we had 3 observational runs, and over those runs we have measured, detected almost 100 sources. For one case, we have seen the electromagnetic counterpart to a source. So for this is a binary neutron star merger, and after the merger, we saw, during the merger, we saw a burst of gamma ray radiation, and then we also saw an afterglow that follows a merger of 2 neutron stars. So now we can do population studies, and this is a much more mature science than, I mean, it's transiting from excitement over each individual detection to population studies and to understanding the origin of these sources and the astronomical scenarios that may lead to. We try to find out how to place them into the realm of known astronomy and known population of stellar objects in astronomy. And this is a plot that shows the current detections. So this eagle-like plot shows like each line shows the merger of one black hole and another black hole into a third black hole. What is very interesting is that we saw some very massive objects, and the reason why I'm saying that it's interesting is that if you look into standard stellar evolution, you do not expect to have black holes that are formed and that have masses above 65 solar masses. But we saw that there are objects above that limit. So this is very interesting, and that places extremely strong constraints on the formation scenarios of these systems, or maybe on the formation scenarios of black holes in stellar collapse. The yellow ones are possible neutron stars, so they have these very small masses, and then their results of mergers are in 2 colors, because we don't really know whether they are massive neutron stars or they are not so massive black holes. And the systems that we see here are all the black holes and neutron stars that have been discovered previously to the gravitational wave detections. So they are detected in via electromagnetic radiation in X-rays, or mainly in X-rays, or also in the radio. The main results are of the gravitational wave astronomy is that we know the existence of binary black holes, binary neutron stars, and we can now really investigate their origin. We have found some compact objects with unexpected masses, and these were these very heavy black holes, but also objects in the mass gap between the neutron stars and the lightest known black holes, between 2 and 5 solar masses. People thought that there is very few, or there are no objects there. Now we know that there are objects there, and this is a big puzzle for astronomy. We know the speed of gravity. We have, since we saw a gamma ray burst together with the gravitational wave burst, spaced only 2 seconds away at the distance of 40 megaparsecs, 120 million light years away, we know that the time difference, time of arrival difference is smaller than that, and therefore we can place an upper bound on the difference between the velocity of light and velocity of gravitational waves. This difference is of below 10 to minus 14, which is much better than the precision with which we know the speed of light. So we know that down to the measurement error, this prediction of GR, that the speed of gravity is the speed of light, works. Then we have the origin of gamma ray bursts. This was always thought to be connected with mergers of two neutron stars. We have now seen a merger of neutron stars that produced a gamma ray burst. We have the origin of heavy elements. So the production of heavy elements heavier than iron in the universe have always been a problem, because in the stars it's very easy to produce all the elements up to iron because you get away energy by producing them. And if you want to produce something heavier nuclei, you need some non-equilibrium conditions. And one of the hypotheses for formation of these elements was that they would be in the matter ejected from supernova explosion. And now, with the observation of a binary neutron star merger, we saw that a small fraction of very heavy nuclei of matter with with very huge content of neutrons was ejected out of this merger. When I'm saying a small fraction, it may be less than 1%, but this is about 10 to the 3 or 10 to the 4 Earth masses, and the press was really happy to find out that in this event about 30 solar masses of gold was produced, so people were excited about this huge amount of gold, but that means that the rate of production of heavy elements in mergers is sufficient to explain the abundance of heavy elements in the universe. So I like to say that if you see this ring has originated in a neutron star merger about 6 billion years ago. And we can now prove the validity of general relativity in the very strong field regime. We can probe general relativity with merging black holes, and the gravity is extremely strong during those mergers. So we can see whether the theory that so far has been only verified in the weak field limit is now verifiable in the very strong field limit. What is the future of this business? So we have several planned experiments like the Einstein telescope, the Cosmic Explorer, which would be next generation detectors of gravitational waves. Einstein telescope is a planned facility of 3 interferometers in a triangular configuration placed underground, and with the arm length of 10 kilometers. Cosmic Explorer is an American idea to make a 40-kilometer interferometer on the ground, and which would be complementary. These two experiments, or these two observatories, would be complementary and would allow us to see binary black hole mergers up to the region before even the stars started being formed, so all the way up to the redshift of 20 or 30. Then, which you can see here, that the farthest object that we have seen so far is this one at z of 0.8. With the improved current experiments, current observatories, we can reach the redshift of 2, but with those we'll be able to see the universe all the way, all the black holes until the redshift of 100, which is well before galaxies and stars started to form. So ET is an experiment I have some warm feelings for. I'm a member of this experiment, and we have a consortium. Poland is a co-founder of ET out of 5 countries. So we do a lot for this future experiment, and there is lots of opportunities for physics graduates with any specialty. Then in the low frequency range, we'll have LISA, which is a space experiment, which will be launched in 2034, and it will look for low frequency gravitational waves with the frequency in the range of millihertz, corresponding to black holes of the mass of about a million solar masses, which you can see here. This is already approved, so this will happen. So to finish, new astronomy is born. New astronomy, new way of looking at the universe is on. We already have lots of interesting results. I believe we'll be able to bring a lot of new results, like looking at the gravitational wave backgrounds, looking at neutron stars, non-sphericity of neutron stars, supernovae, formation of black holes in supernovae, and a lot of other new things. And I'll finish with this picture of merging black holes for your entertainment. And thank you.
Or no? Yeah, it's working. Thank you very much, Professor. And lunch is ready, but we have a time for 1 or 2 quick questions. You're the first. I will come to you.
Okay, 2 quick questions. So at the beginning, you just chose, you used frequency as an input factor for your calculations. Does it get redshifted?
Yes.
So,
yes.
So
yes.
this is another factor for this calculations.
So actually we do not really measure the mass, we measure the redshifted mass.
Okay.
Mass times 1 plus z.
Okay.
But this small redshift, like 0.1, doesn't matter.
All right. And the other question is, does the luminosity depend on the angle of plane of rotation?
Yes, yes. It's these objects are not isotropic emitters. So there is some degeneracy in the angle of the orbital plane and the distance that we see it from.
And the next question, I saw there. Okay.
Okay, so in the last animation that you showed us of 2 black holes merging, there was a moment where the potential was positive, and I was like wondering how to interpret that, whether that's like some kind of anti-gravity or something.
No, it's not. I think that this is the effective potential, which includes the centrifugal force. So at this moment, you can have acceleration of masses that can be modeled by this positive potential. So there are regions that repel that seem to repel the particles, but it's because they are just accelerated towards other directions.
Okay, thank you.
Okay, so let's thanks once again to the professor. Clap, clap, clap. And before we start the lunch, there are one important announcement. We have around 50 minutes to eat the lunch, and we're gonna meet here in this place at 3 p.m. and we will start the marathon introduction, so you have some free time. Bon appetit. And for those who are participating as online, we're gonna meet here at 4 p.m. with the next lecture. Bye. Dziękuję.